So in the beginning of this chapter, you heard me say quite a few times, the first derivative, the first derivative. And then I'd say, well, that's all you know is the first derivative. Well, there's higher order derivatives. And the notation for the higher order derivatives, let's look at our first derivative first. So our first derivative, we could put y prime, we call that prime, and we say y prime. Our second way of saying the first derivative would be f prime of x. Again, this is prime notation. And then we have dy dx. That's Leibniz notation, I believe. And then you've got d dx of a function. That's when you don't have an equation. You're just taking the derivative of an expression. So d dx. And then we've never used this one, this last one, and we probably never will, but maybe when you take a, maybe Calc 3 or differential equations class, that's probably where you'd see it as a differential equations type course. D sub x of y. It's another way to say the derivative. So what would we use for the second derivative? Well, for the second derivative, we'd say y double prime. That's how we'd say it, y double prime. And then f double prime of x. And this is where it gets a little different. We'd say d2y over dx2. So it's not squaring an x, it's not squaring a d, d2y over dx2. If we were just taking the derivative of an expression, and it was the second derivative, d2 over dx2 of f of x, and this funky notation that we've never used before, dx2y. So we use the prime notation with our y and our function notation, and then once we start doing dy dx, d dx, and then that weird looking notation at the end that we've never used, we use the numeral, the number, the Arabic, the Hindu Arabic number 2. That's a true story. That's what our number system is, the Hindu Arabic number system. Okay, the third derivative, y triple prime, and f triple prime of x, and d3y dx3, d3 over dx3, and then you got it, d sub x 3 of y. And our fourth derivative, that's where the prime notation ends, and that's where we start using our Hindu Arabic numbers 4 all the way throughout. The nth derivative, we'll show you that nth derivative, y, and then in parentheses, because we don't want it to be confused with y to the fourth power or y to the nth power. So it's in parentheses, y, nth derivative of y, f of nth derivative of x, and then dn y over dxn, and that's obviously not a power as noted before in the other examples. And then we would have dn over dxn of an expression, f of x, and then d sub x, and then that would be an n up there with a y. So that's our nth derivative. We're going to find the first 5 derivatives of f of x equals 2x to the 4th minus 3x squared. So let's get to it. We've got f of x, I'm going to rewrite f of x right here, equals 2x to the 4th minus 3x squared. And let's find our first derivative. So our first derivative, f prime of x, is equal to 8x cubed minus 6x. And I'm sure you can keep up with me because you've been now finding derivatives for quite a few days now. Not quite a few, but a week. The second derivative is going to be 24x squared minus 6. Our third derivative is the derivative of the second derivative, so that's going to be 48x, and then we've got plus 0. And then we've got our fourth derivative. So look, we're going to put that 4 in parentheses. to show our fourth derivative of f of x is just a 48. And then we will do the fifth derivative by putting that in parentheses. And the derivative of a constant is 0. Hot diggity dog. There's our first 5 derivatives. Okay, example 2. Find the value of g double prime of 2 for g of t equals negative t to the 4th plus 2t cubed plus t plus 4. Now you start looking at this stuff and you're like, I am in the big time now. I'm really doing some calculus here. And you are. You were doing calculus when we were talking about limits and continuity, but you are really now getting into the heavy stuff. Okay, we're going to find our derivative of g of t, our first derivative. So we're going to have negative 4t cubed plus 6t squared plus 1. Then we have to find our second derivative. Our second derivative is going to be negative 12t squared plus 12t, and then plus 0, so we're not going to write that. And then we get to find g double prime of 2. So now everywhere I see a t in g double prime of t, let's make this red. I should have just changed the color, right? I got that magic pen that can do that. I should have just changed the color. G double prime of 2 is equal to negative 12 times 2 squared plus 12 times 2. Everywhere you see a t in the second derivative, you're going to put a 2 in its place. And negative 12 times 4 is negative 48. And 12 times 2 is 24. So g double prime of 2 is equal to negative 24. So easy, a caveman can do it, right? Okay, let's try example number 3. Let's find the first 4 derivatives of y equals x to the negative 1. Now, we've practiced this. This is 1 over x, so we can do this, and you're going to see how this is some really good stuff. Okay, let's rewrite y equals 1 over x, and let's just practice with that 1 over x. Okay, y prime is equal to the opposite sign, 1 over x squared. And then y double prime is equal to the opposite sign, so it's going to be a positive. We're going to take that exponent of 2. 2 times 1 is 2 over x cubed. Yay! And if you didn't realize this, you're realizing it now. The third derivative is going to be the opposite sign, so now we're at a negative. 3 times 2 is 6 over x to the 4th. It's true. It really works this way. And then our fourth derivative, remember we need to put that parentheses around our fourth derivative, is equal to a positive 4 times 6 is 24 over x to the 5th. And there's our 4 derivatives. There's our 4 derivatives. And I'm going to actually shrink this. Let's move this up and let's resize this. So it's, there we go. Good. Let's move it. There we go. And let's move this so that I can keep it all together here, because this is some good stuff. You got to admit, this right here, if you didn't see it before, that's how the fractions worked, hopefully you just saw it just now and you said, whoa, okay, that's pretty cool. And then maybe try one on your own. Make a problem up and try it, and then give it to a friend and have them check it. There's your first 4 derivatives. Okay, velocity, we've talked about this. Velocity is given by the first derivative of, and I know some of you can say it because you said it before, the position function. It is the first derivative of the position function. The rate of change of the position with respect to time is the velocity. Okay, so saying it forwards, velocity is given by the first derivative of position. The rate of change of position with respect to time is called the velocity. And notice how we're saying rate of change, not average. We're saying rate of change. So we're talking derivatives. Okay, similarly, the rate of change of the velocity. We've done this one before, but only once. So if you were paying attention, you might get this. The rate of change of the velocity with respect to time is defined to be the acceleration of the object. Acceleration. I think I got that right. Acceleration. You're telling me, but I'm not hearing you right now because you're watching the video. I'm going to change this color to red. Do you know why I just changed it to red? Because velocity is not the same thing as position. So I want velocity to be a different color, and then I want to link it down here and say, your derivative of velocity is acceleration. So what can we say about the position function? If I've got the position function with respect to the acceleration, acceleration is the second derivative of position. So let's write that down. We've got s of t equals position, and I'm going to use the colors I used above. Velocity, here we go, velocity is red. That's your first derivative. And then your second derivative of position is acceleration. Much easier to spell when I'm doing upper and when I'm doing lowercase. Much easier to see that. So I could say that the first derivative of velocity is v of t. And I could say that the first derivative of velocity is acceleration. So all of these are synonymous. Acceleration with respect to time is the first derivative of velocity, which is and acceleration is the second derivative of the position function. Cool stuff. So now we can put it together in this problem. A ball is thrown upward from the top of a 160-foot cliff. The initial velocity of the ball is 48 feet per second. So here we are on a cliff. And then boom, what's a cliff? It just drops. And here we are, someone's standing there and they throw the ball. Not too much where they jolt their body because they're going to fall off the cliff and they don't want to fall off the cliff. So they're going to throw the ball with an initial velocity of 48 feet per second, which means it's going to go up first and then it's going to drop and it's going to fall. And this height is 160 feet off the ground. So this is the ground level there at the top of the cliff. The position function s is equal to, I'm going to let you write it down, so get a little bit ahead of me, stop your beautiful drawing and write that position function down, negative 16t squared plus 48t plus 160. T is measured in seconds. Find the height, the velocity, and the acceleration of the ball when t equals 3. So let's start with the height. The height of the ball when t equals 3. Well, this is just algebra 1. This is s equals negative 16 times 9, because 3 squared is 9, plus 48 times 3, plus 160. So this is negative 144 plus, I believe that's 144, plus 160 is 160 feet. So what's happening is that it's taking 3 seconds. So it's taking, I should have drawn it the other way. This right here is 3 seconds. It's a horizontal length of 3, which relates to the time in seconds. So you throw it up and it's up in the air, up in the air, up in the air for 1 Mississippi, 2 Mississippi, 3 Mississippi, and then where is it? It's right there at the same level at which it was thrown, 160 feet. Okay, I'm going to come back and highlight that. Un momento. Okay, then we've got our velocity. Our velocity at 3 seconds is going to be the first derivative Woohoo! This is not function notation. Our first derivative, which is negative 32t plus 48. You just go to the position function, find the derivative. And now I'm going to say at 3 seconds, negative 32 times 3 plus 48. So that, I believe, is negative 96 plus 48. And that is negative 48. Velocity is going to be in feet per second. And the negative means that it is on its way down. So positive would be the original direction, which was up. And then negative is the direction that's opposite going up, which is going down. And now we have our acceleration. So our acceleration at 3 seconds. So that's going to be the second derivative of our position function. So we're going to go to our first derivative and find the derivative of it. So that's negative 32, and it's a constant. So it's negative 32 feet per second squared. And that right there reminds me of some trigonometry with secant, but it's not secant, it's a second. So what does that mean? It means 32 feet per second. So your rate of change with respect to time. Okay, let's go back here because this is important. Your rate of change of velocity. So velocity is measured in feet per second, right? So this is your velocity. And your rate of change of velocity, so your change in velocity with respect to time, which is measured in seconds, is feet per second per second. And feet per second, can you tell that this is pretty cool stuff? Feet per second is feet per second squared. And we're ready for the highlighter. That's our answer for acceleration. Let me go ahead and underline acceleration so it looks all pretty. And this is our answer for our velocity at 3 seconds. And this is our answer for height after 3 seconds. Now, will the acceleration always be negative 32 feet per second squared? You bet your bottom dollar it is, because it's a constant. It's never going to change. So the rate of change of acceleration is a constant. I'm sorry, the rate of change of velocity is a constant. The rate of change of velocity is a constant, and the rate of change of velocity is acceleration, and acceleration is going to be a constant. So what's the acceleration of the ball at any time? Hopefully, you know what color I'm going to pick. What color am I going to pick? I'm picking purple, because it is always going to be negative 32 feet per second squared. So I think here's one for you that you may be able to try. Let's try this one. An astronaut standing on the surface of the moon throws a rock into the air. The height in feet of the rock is given by S equals, okay, so think about this, S equals negative 27 over 10 t squared plus 27t plus 6. So what I want you to think about here is, why am I not using negative 16t squared plus 48t plus my initial height? Well, the reason being is because gravity on the moon is a little different, right? So that negative, that pull, that gravitational pull that's pulling the ball down when you throw the ball off the cliff. I don't know if I said bull or ball. Whether you throw a bull or a ball off a cliff, it doesn't matter, because that gravitational pull is what's pulling it down. Well, things are different on the moon. This is our equation for the moon. And this equation would be given to you. So how does acceleration due to gravity on the moon compare with that on the Earth? So let's try this. So S prime of t, or just S prime, because there's not function notation, is equal to negative 27 over 5t plus 27. And that's our velocity. Hopefully you can see that. That's our velocity. And then we have our acceleration, which is the second derivative of our position function. And that's equal to negative 27 over 5, which is approximately negative 5 point, let's see, 2/5 is 4, 5.4 feet per second squared. So let's think about this. Negative 16t squared, that's your negative 16t squared, and then we've got that negative 32t, and then we've got negative 32. So negative 32 feet per second squared. That's our acceleration on the Earth, right, due to gravity. Negative 5.4, much less. So you throw the rock, you throw this moon rock up in the air on the moon, and what do? You're sitting there, you're not watching it fall like you do on the Earth. You're watching it kind of float down. And the reason why you're watching it float down is because we're so used to acceleration due to gravity being negative 32 feet per second squared that it seems like it's floating down to the ground, because on the moon you've got a different gravitational pull. Okay, example number 6. The velocity v in feet per second of a certain automobile starting from rest is 80t over t plus 5. Okay, so this is the velocity of a certain automobile. They're giving you the equation. We did not have to derive this or find it, nor do we ever need to know it. We want to find the acceleration. Okay, so we're going to find the acceleration. So v is equal to 80t over t plus 5. To find the acceleration, we are going to have to find the first derivative. So we're going to take the derivative of the numerator, which is 80, times the denominator, minus the derivative of the denominator, which is 1, times the numerator, all over the denominator squared. So we have v prime, which is our acceleration is our first derivative of velocity, is equal to 80t plus 400 minus 80t all over t plus 5 quantity squared. So that would be 400 divided by t plus 5 quantity squared. That's the acceleration of this particular automobile starting from rest, where time is time in seconds. So this would be 400 over t plus 5 quantity squared feet per second squared. And that's our application of higher order derivatives. So now you can see why it's important to have that second derivative. And in higher order math, we're going to maybe use the third, fourth, fifth derivative, and so on. But again, usually that happens in a higher level calculus class.